Okay, hello everyone. Welcome back to the lecture series on expectation value of a physical observable quantity in quantum mechanics. In our last two classes, we have been discussed in detail about representation of expectation value of a physical observable A and some important questions on expectation value. In today's class, we are going to discuss using expectation value, we have to verify Heisenberg uncertainty principle. In our first class, we discussed why and how the expectation value of a physical observable A is represented by this format with the help of two examples. One is a group of students, and by considering discrete mass distribution on a rod, we discussed in detail that why and how the expectation value of a physical observable quantity A is represented by this one. In our last class, we discussed three numericals. We found the expectation value of the position of one-dimensional box or one-dimensional dynamics of the particle, like along x-axis. If it is dynamics uh, like this from x equal 0 to L, what will be its expectation value? We have been discussed detailed, and we found the expectation value will be L by 2, or the most probable position of the particle. What we found, L by 2 at the middle of this length of this rod, and then we calculated the expectation value of the momentum, and we found the value is 0. Then we calculated the expectation value of total energy. We found n square pi square h square square by 2m L square. In detail, we have been discussed in our last two classes. In this class, we are going to discuss verification of Heisenberg uncertainty principle by using the results whatever we found in our previous two classes. Right. So let us start. So this expression or Heisenberg uncertainty principle, we have to verify with the help of our previous results, where this one delta x cap and delta px cap, or it is written also del x and del px, most of the book, are the uncertainty position and momentum. Uncertainty position also can be written as deviation of position from its mean value, and this one uncertainty momentum also can be written as deviation of momentum from its mean value. So this is the quantum dynamics. Suppose we are going to consider a quantum particle moving along x-axis from x equal 0 to x equal to suppose L length. Then we have to find out its uncertainty position and uncertainty momentum, or what is the value of deviation of a position from its mean value. We know that the mean value of uh, or expectation value of position is this one, and expectation of momentum is this one. So these are the deviation from the mean values. If I will multiply these two, then it will be always greater than equal to h cross by 2. That we are going to verify. This is famous principle given by Heisenberg, right? If we are going to consider the mathematics, in general, deviation or standard deviation, also it is called a standard deviation, represented by sigma, denoted by sigma, it is represented as root over of variance. So what is the variance? Mean of squares minus square of the mean. So here you can see square of the mean. Mean value is nothing but this one, and its square is this one. Mean of the squares. Mean of the squares means squares mean expectation value of squares. So this value minus square of the mean. Or we can write mean of the squares means first we have to add the squares divided by total number minus square of the means. First you have to find the mean and take the square, and its whole root over is nothing but deviation. In quantum mechanics language, already I discussed, this one can be written as in this format: expectation value of square. This is square of the expectation value, whole root over is the deviation. If we are going to consider the position, deviation of a position, then it will be represented by this one, del x cap. This is sigma. Here nothing but del x cap deviation is this one. If I am going to consider the momentum deviation, del px cap, instead of x it will be px square minus px cap square root over. Okay, previously in our previous lecture we found expectation value of position for this dynamics is your L by 2. If we are going to consider x equal to 0 to x equal to L, at exactly L by 2 is the expectation value of the position. Expectation value of the momentum we found 0. So this value and this value is your how much? L by 2 we know, and we have to just write L by 2 square, and this value is 0 already we know. To find this deviation or uncertainty position and uncertainty momentum, we have to calculate this value and this value, right? Same the procedure is the same. So we have to calculate expectation of x square. So what we have to write? The format or writing format is same, 0 to L. We are considering same dynamics, that particle is moving from x equal to 0 to L. Okay, 0 to L, to one fro from 0 to L, length is L. So limiting value, lower limit will be 0, upper limit will be L psi star x square psi dx. So here x cap is your x, so it will x square psi dx. We have to just substitute psi star value already given in the question. You can follow the last class video, uh, that you can found this one psi also this much x square, right? You have to calculate same way here, 2 by L, 2 by L. So outside it will be 2 by L, then it will be x square sine square n pi x by L dx, and use the by parts, and finally you can found this answer. So I suggest to do by yourself. Here I written do by yourself. The steps whatever I told to you, you just do by yourself in your rough. Finally you can found mean value of square equal to L square by 3 minus L square by 2 n square pi square. Okay, now we have to find out. Now if we are going to consider uncertainty position or the deviation of position from its mean value, that means del x cap is your root over of this minus this, square mean and mean square. Square mean, how much we found? This one I written, minus this value. This value already we found, uh, is your L by 2. So L by 2 square, right? Here you can see, if this is your L by 3, this will be, this is L square by 3, this is your L square by 4. You just subtract, you can found L square by 12 minus this much, right? Right. Here we found del x cap. Del x cap value is this much. Now we have to find out del p x cap. For that we have to find out px square. Okay, so how we have to uh, calculate this one? Same procedure, integration 0 to L psi star px cap square psi dx. Px value is your I h cross minus I h cross del by del x square psi dx, and this value will be this much. Do by yourself. Here easily you can found this much. How? May you remember that total energy operator was how much for this case? If we are going to consider for one dimensional box moving from x equal to 0 to L, you just follow the last class video. 0 to L, total energy operator is nothing but kinetic energy operator plus potential energy operator. Potential energy inside this box is 0, so kinetic energy operator. Kinetic energy operator is your how much we found? We have to write minus h cross square by 2m del square by del x square, right? So here you can see, if I am going to square this one, this is nothing but h cot square by h cot square del square by del x square, right? So here px square, if I'll be consider, this will be this much, and here in this way also it is minus h cot square del square by del x square, and this value if I will compare this value, only 2m is in the denominator. Okay, for total energy we found expectation value of total energy, what we found? N square pi square h cot square by 2m L square. So here this 2m value, how it came? Due to this one, but in this case this 2m is absent, so what will be the value? Only 2m will be not there, and other terms will be there. Okay, so n square pi square h cot square by L square. So if you want, you can also derive step by step, no problem. Got it? Okay, now we have to find out uncertainty momentum or deviation of momentum from its mean value is what? The square mean minus mean square, root over, whole root over. And this is value how much we found? This one I substituted. Okay, minus this value we found 0, px value 0. So obviously this term will be 0. I not written that one. Now you just multiply uncertainty momentum value this much into uncertainty position value this much, what we found in our last slide. I'm going to show you uncertainty position value or deviation of position from its mean value is this much. This much I have been written over here, and uncertainty momentum value this much, here it has been written. Okay, now you just multiply this factor with this one. Here L square got cancelled, and we found n square pi square h square square by 12, and multiply this term with this one. We found n square L square got cancelled, n square pi square h square by 2 n square pi square. Here pi square n square got cancelled. From these two terms, just take a common h square by 4. So if I will take common h square by 4, remaining terms will be n square pi square by 3, and taking common from these two terms h square by 2, h square by 4, then it will be 2, right? Right. So here you can see, if I am take the root over of this one, then the value will be how much? The value will be h cot by 2 root over of some positive value, here you can see this value obviously greater than 2, because this value is 3 point pi value 3.14 into 3.14, so it will be approximately 9 plus greater than 9 by 3 greater than 3. So this value obviously, this bracket value obviously positive value. Okay, hence del x cap into del px, uncertainty position into uncertainty momentum, will be greater than, here root over of h cot square by 4 will be h cot by 2, and this value is approximately 1, approximately greater than equal to 1 if you are going to calculate, right? So we found this expression, which is nothing but your Heisenberg uncertainty principle. Hence we can say the verification, this is the verification of Heisenberg uncertainty principle, right? Where del x, or you can write del x cap itself, del x and del px, here you just write del px because we consider along x-axis, del px are represent the uncertainty position and momentum of the particle respectively, right? So here we verified the Heisenberg uncertainty principle by considering one dimensional dynamics from x equal to 0 to x equal to L. The wave function, what we consider 2 by L root over sine n by x by L. This is the generalized or normalized wave function of 1D box, one dimensional box. By considering this one, we verified. This is very important for your exam point of view. This question asked oftenly 4 to 6 mark. So procedure, what is the procedure? Procedure that you have to find out del x and del px. Del x is nothing but your root over of x square mean minus x mean square. In short, you have to derive del px, you have to derive, and after multiplication up to this much you have to write for 4 to 6 mark. Okay, now suppose this verification asked for one dimensional linear harmonic oscillator. Suppose linear harmonic oscillator, suppose we are going to consider generalized normalized wave function of linear harmonic oscillator, that is your alpha by 2 to the n into n factorial root over of pi to the power 1 by 2 h n alpha x okay, into e to the power minus alpha square by x square by 2. This is the normalized wave function of a linear harmonic oscillator. So if this is a linear harmonic oscillator which is oscillating about its mean position, this is the normalized wave function. And here this is the Hermite polynomial. And suppose in your exam asked that by considering ground state normalized wave function, suppose if we are going to consider the ground state wave function of linear harmonic oscillator, one dimensional linear harmonic oscillator, psi naught will be how much? It will be here instead of n we have to put 0. So 2 to the power 0 is 1, and it will be alpha by n factorial means 0 factorial also 1 root by to the power 1 by 2, and h0 is your 1. This value is your 1 into e to the minus alpha square x square by 2. Suppose this wave function has been given, and you have to verify or you have to prove the Heisenberg uncertainty principle. So what you have to do, you have to find out expectation value of x, same procedure, expectation value of x square, expectation value of a px, expectation value of a px square, and delta x is nothing but root over of x square mean minus mean square, and delta px you have to find out this one, then you have to multiply, and you can see that you will get this result. Okay, do by yourself. Thank you so much for watching this video. If you like, subscribe and share with your friends. And here, download the whole note whatever we have been discussed in these three videos. Download the note, link I given in the description. Okay, thank you once again for watching this video. Thank you.